Hi guys, in today's video we're going to first of all in a 26-minute part of this tutorial show you how to run logistic regression in theory, and at the end of the tutorial we will show you how to implement this method in SPSS. So just listen to the first part of this tutorial, which is based on the theoretical foundation of logistic regression, how to estimate coefficient using maximum likelihood method, how to interpret them in terms of odds ratio, and so on. At the end, we will present to you the implementation of logistic regression in SPSS using bank data based on reputation that is logistic regression that can lead to the management model to use by the bank in order to help take a decision of giving loan or not to bank clients.
Contextually, you need to know that logistic regression is applied in case in which we have a qualitative variable with two modalities. That means the variable is binary. The binary variable that we need to explain using k, qualitative or quantitative variables. So the explanatory variable is qualitative with two modality or being binary. That means that's the foundation of logistic regression. And to explain your binary variable, you need to have explanatory variable in the number of k that can be qualitative or quantitative in order to explain your variable. So logistic regression is mostly used in epidemiology in order, for example, to identify the disease related factors, or to search for the death causes or patient survival. So you need to know what cause a particular disease. You have factor that can be related to the disease. You can make a binary or a simple logistic regression in order to see what influence the occurrence of your disease using factor that are explanatory variable that need to be whatever qualitative or quantitative. So what's the specification of the model? So as I told you very earlier in this tutorial video, y is a binary variable that have two modalities: 0 in case of non-occurrence of the situation, and 1 in the case of occurrence of the situation. Y is supposed to be random, and your explanatory are supposed not to be random variables. Then the m of the of the simple linear simple logistic regression is to explain the occurrence of a phenomenon. So the phenomenon that is binary, that have only two modalities: success and other eventuality. So we are looking for the probability of success. If our first modality is success, for example, we are searching to estimate the probability of success. And you need to know also that in simple linear regression, or generally in logistic regression, we work in terms of expectancy. So the main objective is to predict or to explain a categorical variable y from recollection of descriptor variable that can be enumerated as x1, x2 till xk. It's sort of like highlighting the existence of underlying function link. So we are searching for a underlying function link between our our explanatory variable, that is binary variable, in function of descriptors. So you need to know that in this kind of specification, our function that related y to the factor to the descriptor cannot be a linear function because y take only two variables. So you cannot use linear function. Linear function is not required, is not appropriate. It's not appropriate in this kind of situation if you need to explain your main variable that is supposed to be binary in function of many other variables, even though there was only quantitative. So we need to search for a functional relationship that cannot be linear in this kind of situation. So when you look at the expectancy of y, taking only two variables, once use a logistic function. The logistic function is a function that's defined by the ratio of exponential of a number over 1 plus the exponential of a number. That's take the form of a probability, because this function take its value between 0 and 1, and it's a positive, the expectancy is equal 0 to 1. So we can use logistic function defined as so in order to model the probability of that is binary, to model the probability of occurrence of our phenomenon that is that only have two possible realization. Y distribution, we can say that y follow the Bernoulli's law of parameter p. P is the parameter that we are going to express to estimate using a logistic function. So if we have two modality, we can suppose that our variable follow a Bernoulli law of parameter p. And if we apply the logistic transformation to our probability, we can see that logistic can be written as a logarithm of our parameter. Parameter that we previously expressed in function of in terms of logistic. We can also find x in this relationship in order to you will find the relationship that give the logic in function of your parameter. So the challenge in the logistic regression is to estimate a coefficient. As you see, when we make a transformation of our parameter, you see that our parameter is a relationship that is not now only 0, 1 realization, but the logarithm of our parameter is a relationship that can be take its value in R. So we can use linear regression right now in order to make to model a logic of our parameter, because our parameter take its value in R, in numeric number set. So the challenge is to estimate beta 0, beta 1 till beta k, so that the logic of our parameter that is expressed like that can be written correctly. So what can we estimate logistic coefficient? In multiple linear regression, the method of the ordinary least square is known as minimizing the sum of square of error, error square, and this method is not appropriate. It's not interesting in the case of logistic regression. So we will use in logistic regression a classical method of maximum likelihood. That is a method that allows to estimate a parameter of a law or a model. So we use maximum likelihood method in order to estimate parameter, and we will come back in this method in a second. So we'll just take an example of binary variable that have only two modalities, 0 and 1, and we have only one explanatory quantitative variable x. So we have our population, we have an n sample of our variable. So we have a n couple of variable xi and xi yi xi. So we are going to use this sample in order to estimate our parameter. We have for each observation I, the variable yi is equal to 1 with the probability p of x equal to the probability that y take a value 1, knowing that x take a value xi, and 0 with odd probability. So defined as so, y follow the Bernoulli law with parameter 1 and the probability, so that the probability is given by the logistic function that define a probability that can be used in order to define the probability. So in likelihood, in maximum likelihood method, the first thing is to estimate the likelihood of our joint function. The likelihood is a probability that to observe our sample, So that which means that for every of our n independent variable, the likelihood is equal to the probability that x1 take a realization of our variable for the first observation, x2 take a realization of our variable to the second observation, and so on. So using the independence of our function, we can write our likelihood as a product of every probability. So since the observation are considered to be independent, we can write our likelihood as a product of every single probability. So if we use a Bernoulli law, we can write our probability for every xi as you see on your screen, so that the likelihood can be written as a product of every single probability. But if we use a logistic model that is given as follow, as we show you very earlier in this tutorial video, we can write a likelihood as a function of alpha 0 and beta 0. So the objective of the maximum likelihood is to maximize the probability to observe our sample, to maximize our likelihood function that is written as so. So for the reason of simplicity, we will just run the maximum of the logarithm of our likelihood function, that is the same as the maximum of the likelihood, given that when we calculate the logarithm of our likelihood, we have a function that is very easy to manipulate. So to find the maximum of our the log of our likelihood function, we use numeric method called Newton-Raphson in order to search for beta 0 and beta 1 that maximize our likelihood. That's the point that annul the partial derivative of our log likelihood function. So the interest is that once beta 0 and beta 1 estimated, we can calculate for all I the probability of success given the different observation. So with the logistic model, we can write the logic of this probability as a combination of our estimated parameter. So once we have compute our coefficient in our logistic model, one of the main challenge is hypothesis tests on our coefficients. First of all, the global test of significance of our model, and to test this, we will use our likelihood ratio test. Likelihood ratio test in which we have null hypothesis, no connection between y and the xi. That means that we suppose that every coefficient is in our linear model, is in our logistic model null. That's the null hypothesis, and its alternative is that the model makes sense. That means that at least one coefficient is different to 0. So to test this hypothesis, we can consider a simple example, the case with a single explanatory variable. We can come back to the single explanatory variable. So the principle of the likelihood ratio test is to compare the likelihood x with explanatory variables on the H1 the hypothesis with the likelihood L0 without explanatory variable, so is under the null hypothesis. Intuitively, we can think that if likelihood on the H1 is superior to the likelihood on the null hypothesis, then the variable bring to estimate the estimate of the probability of y. So the in livelihood test, we consider a statistic D that is given on our screen that is shown to follow the chi-square at 1 degree of liberty. So the interpretation is that the non-rejection of H0 in case of non-rejection of H0, the model does not make sense. Does not make sense at anything to do estimate of probability of Y. So model doesn't make sense. That mean that we are wrong, supposing that the logic of our probability is a linear combination of our explanatory variable. So in the other hand, the rejection of our null hypothesis means that the model makes sense, given that X give the estimate of our probability. So there exists a link between our probability and our explanatory variable. So also to interpret our coefficient, we can remind you a notion about odds ratio that you can find on my previous tutorial. The odds ratio that is defined as a measure of association between exposure and between exposure to the disease and the disease himself. So the odds ratio is calculated and the ratio of those probability, the ratio of odd to be exposed. The odd to be exposed is the ratio between the probability of exposure and of exposure that are sick and the exposed person that are not sick. And the odd ratio of unexposed is a ratio between the probability of non-exposed that are sick and non-exposed that are not sick. So after odds ratio calculated, we can be using it in order to interpret our coefficient. So you need to know also that when the odds ratio is when our probability, the probability of to be sick is low, inferior to 10%, the odds ratio is sensitively equal to the relative risk. So the odds ratio can be calculated and interpreted as follows. When the odds ratio is equal to 1, you can suppose that there is not association between our disease and the exposure. There is not association. And when the odds ratio is more than 1, we suppose that exposure is a risk factor to the disease. And rather, when odds ratio is less than 1, the exposure is a protective factor to the disease. So we can use, we can conclude that odds ratio is equal to 1 when chi-square association test is not significant. So to interpret a coefficient, we will take we can also see that in single explanatory variable, the logic of our explanatory variable of can be written as a combination of x variables. So the difference between the logic of the probability of to have the first modality of our explanatory variable and the logic of the probability to have the second modality of our variable is equal to beta, so that the logic of the ratio of probability of success and the odd event is equal to beta 1, and we obtain our odd ratio as an exponential of beta 1, so that the exponential of the coefficient can be interpreted as an odd ratio. We will return that odd ratio as we show the calculation very earlier a minute ago, is can be interpreted as a exponential of beta 1. So we can notice that same in the multiple case, but the odd ratio are adjusted on the other variable xg. So we suppose that x is quantitative variable, odd ratio equal to exponential of beta 0. We can have this interpretation in this particular example where our odd ratio is equal to 2 when we have as variable age in tens of years. If we have as explanatory variable age in tens of years, we can show the following interpretation when odd ratio is equal to 2. So going from 20 to 30, multiply the risk of disease by 2, or age 16 to 17, double the risk of illness. And this is underlie the strong hypothesis that the log linearity, under the hypothesis of log linearity of each wish of x, which is to be verified. So that's
we have made a series of videos on binary logistic, but just in theory. We show you how to estimate coefficient and how to interpret them, and as well as the method that is being used in order to estimate coefficient of logistic regression, and so many other notions. But now we are going to show you how to implement a binary logistic in SPSS. So binary logistic, as you know, is a method used to explain binary phenomenon. The phenomenon can be a disease. So we search to explain what causes, for example, a disease. Is it due to to each or other parameter? So binary logistic, we can also search for for example, of a disease. So we can use logistic regression in order to analyze what factor is influence significantly the disease, the appearance of disease, which factor is a risk factor or a protective factor. So in binary logistic, we will show you how to run it, as well as the interpretation of estimation results. So if you are going to run a binary logistic, so you will use a tab analyze. So when you are in analyze, you go on regression, and you choose binary logistic. Binary logistic. In this case, we are going to use binary logistic in this example to explain client reputation in bank sector. So in bank sector, you can define a variable called reputation in order to explain whether or not a client is good or not for a bank. So if you are in a person that have bad reputation based on your future loans, based on your based on your habit vis-a-vis your bank. So the bank can class you in good or bad reputation side. So we are going to use uh, this reputation, this variable called reputation, in order we are going to use other variable on our database. We can be sex, gender, can be gender and age, for example, in order to help you explain whether or not a client can be good or bad reputation. And this is a model that can help you uh, to know whether or not to give a loan to a client or not if you are a banking sector. So when you go on the analyze regression and binary logistic, you show this window. So here we need to put a dependent variable. Our dependent variable is now is a reputation. So here is our variable reputation that we select on our variable list and use this arrow in order to click this arrow, and the variable will go on dependent variable. So to explain the reputation of a client, we choose in the first case the age which is a quantitative variable. So as age is quantitative variable will not change here in categorical. This tab categorical. If sex is age was categorical, we should have used this arrow in order to put age in this area. So as age is quantitative variable, we'll just let it like this. So our dependent variable is reputation, and our covariant is age. So there are so many options. We just click on OK. So we'll come back a little bit sooner on it. So we'll just go back in the final result, the last table that is that we are seeing on our screen. So we have our dependent variable, the age, and the intercept, the constant. So here is the significance of our variable. So the age at 10% level is not significant. So here is the exponential of b, that what we call in our theory, theoretical tutorial, the adjusted odd ratio. So having if age was significant, we could have said that age is a protective factor. So which means that when age increase, the probability of being in bad reputation decrease. So age is a good factor. So bank will also need to make most confidence in participation in clients that are more age. That age is very much higher. So we'll come back on our tab analyze regression, binary regression, binary logistic, and we show that we can save so many other options. We can go on option, so we can click on interval, confident interval of the odd ratio of the exponential of b at 95%. So we can change this threshold. So this threshold means that we are searching for 5% significance. So we can put 19% in order to say that we are searching significant at 10% level. So the probability threshold is 15%, and removal threshold is 10%. So we click on OK, and we will see that in our last table here we'll have the confidence interval for the exponential of b, as we didn't have in this last result table. So we click on continue and we click on OK, and we'll see that there uh, our variable age maybe not significant at 10%. You can see that the odd ratio is there on our table. So if age was significant at 10%, if we consider that age is significant at 10% level, we can affirm that age increase lead to decrease of chance to be a bad reputation client of a bank. So we will go on a little bit deeper in our analysis and in order to show you uh, what age category can most influence in the probability of being good or bad reputation. Because before that, we will show you the classification table. This is the classification table of our probability, which means that we have 6% in our sample that were in good reputation that are now in good reputation. So we also have 11% that 11% that were in good reputation that are classed in bad reputation. That means that our percentage of be in bad reputation, the classification percentage of correct is just 35%, which means that our model is not very good. So we'll come back on categorical age classification. So we have class our age, as you can see on in this in our database. We have class age between three categories. We have a category of clients that are aged between 28 and 35. We have 36 to 45, and we have more than 45 age old year old. So this variable take the value 1 if you are in the age 28 35 is a variable that take a value 1 if you are in 28 to 35 and 2 if not, and the variable 36 to 45 take 1 if you are in 36 to 30 to 45 and 2 if not. So lastly age more than 45% took the value 1 if you are more than 45 year old and 2 if not. So we'll analyze, we go and analyze regression and binary regression. We remove our variable age and just put our variable age 28 35. So we'll go on categorical, which to select our variable and use the arrow to put it in categorical covariate, because age 28 35 is a qualitative variable. So we click on continue. In option, we also have confidence interval. So we continue. We can also save, for example, the probability of predicted value. So we'll just let it like this for now. So we click on OK, and we have a result of age 28 35. So which means that you see that the adjusted odd ratio is more than 1, even though age 28 35 didn't significantly influence because p-value is superior to 10%. If we take 10% level, you can see that age between 28 to 35 is risk factor because odd ratio is more than 1, which means that odd ratio of 2.16 mean that belonging to this age group multiply the probability of being in bad reputation by 2. So the bank should very look at persons which are aged between 28 to 35 before allowing them to have a loan. So we'll do the same thing in other groups, other age groups. We'll take age 36 to 45-year-old group and click on OK, and we see that it's not also significant, but you see that in this category the old ratio have decreased. It's less than 1, which means that person in this age group can be have more probability to be in bad in good reputation sites. So we look at the last age group, which is more than 45-year-old. So we put more than 45-year-old in our regression covariant and choose categorical. So in this case, we will say, for example, we go in save and say probability of prediction of our model. So we click on OK. We see that in our final table, old age more than 45% influence significantly to the appearance of a factor of reputation, influence significantly on reputation, and is a protective factor because old ratio is less than 1. So odd ratio of 0.3 mean that when belonging to group age of more than 45-year-old decrease the risk of being a bad reputation client. So when you belong to person which are in this group age are at 0.3 times less have 0.3 times less chance to be in bad size population, which are those who are on bad reputation side. So being aged between 45% is a good thing for a bank because the client are more likely to be in good reputation side. So we can see the odd ratio, which is between 0.1 and 0.96, which is a good sign that at 10% level we can affirm that age more than 45-year-old is a good thing for a bank. We can see also in our classification table here that probability of being in the good to be well classified by the model when you are when you are the probability of being well classified is 58% and 68% in good and bad side. So we have just remember that we have click on the icon save probability. Save probability. We go on our database and we see that last column of our logistic regression that the probability of prediction of being in one has been computed by SPSS here. So you have the probability of being of the every client to be in good or bad to be in bad reputation, which is here. So you can use it to analyze your regression logistic using the fact that the threshold is 50%. That is the threshold that is used to classify people in good or bad reputation. So that's it for today.